Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be finishing up our notes from Chapter 11, looking at energy problems. Now, one of the things you need to understand is we've done some of this before, so really only some of this is going to be new. But when we look at how we calculate energy in physical reactions, one type of physical reaction that's specific to this chapter would be a change of state. We didn't look at how to calculate energies of changes of state back in our energy chapter, chapter 5. So this one is actually going to be new. The second one, however, is exactly what we did. Q equals mc delta T would be the equation we use if we're just warming up or cooling down a single state. So that's how we calculate the Q when we're not undergoing a change of state, when we're adding energy or removing energy within a single state. And then the third situation is when we do both at the same time. And I typically refer to these as complex energy problems because you're going to be doing combinations of 1 and 2. And worst case, this could be as many as a 5-step problem. If you are warming up a solid, melting the solid, warming up the liquid, boiling the liquid, and then warming up the gas, you'd actually have 5 different energy calculations to do that. Now, when we're looking at the change of state region, so this is a temperature versus heat added, looks very similar to the temperature versus time graph that we looked at earlier in the chapter. So this is looking at adding heat over time and what's happening to the temperature. Notice at the beginning here from A to B as we're adding heat. In that section, the temperature is going up. So that must mean we are warming up something. Because as we add energy, the temperature is changing. So that's not a change of state. That's when we're within a single state. In this case, it would be ice. But notice in regions B to C and D to E, they've plateaued. So even though we're still adding energy, our temperature is not changing. Remember, that's the dead giveaway that we're at a change of state. So heat added to the system at our change of state, like melting and boiling, is going to not speed up the molecules, but to break intermolecular forces. Partially break in the case of solid to liquid, and then completely break in the case of liquid to gas. As we're moving the molecules farther apart, partially and completely, yes, that takes energy, and therefore the energy is going to break intermolecular forces. And the temperature at those points are going to be constant. So remember, whenever you're looking at a temperature time or a temperature heat added graph, the plateaus are our change of state regions where our temperature is constant, and therefore kinetic energy is not changing. What's changing is the potential energy of the system. So in these regions, B to C and D to E, it involves changes in potential energy. The system is increasing in potential energy as we're breaking in D to E and partially breaking in B to C intermolecular forces. Now, the energy in these regions for a change of state would be calculated differently than we did in Chapter 5. It's a slightly simpler equation. It's just the heat of the reaction. These are typically listed as molar heats. So that if it's a molar heat, it would be the energy per mole. So how many moles are reacting? But heats of reaction are given as energy per gram. So the big thing is, it's either the delta H of reaction times moles or mass. Look at the units of delta H, and that's going to tell you what you're doing. Most of the time, they're molar heats when we're dealing with delta H's. So if it's a kilojoule per mole amount, you know you're going to multiply by the number of moles. If it's a kilojoule per gram, you're going to multiply by the mass in grams. But most of the time, you're going to see molar heats for these. And the one thing you need to realize is, related to units, it's also always going to be kilojoules. If you remember back in Chapter 5, whenever we did anything with delta H's, they were always in kilojoules. And that's going to present a problem in a complex reaction that we're going to have to look at. So here's an example of doing one of these change of state problems. Calculate the energy needed to melt 248 grams of H2O. All we're doing is melting it, so it must be at 0 degrees Celsius. We don't have to warm it up. We're just going to melt it into its liquid form. Now you'll notice there's a bunch of heats of fusion, heats of vaporization. There are also 3 constants with C, specific heats of ice, water, and steam. So we've got a lot of constants, and we just have to realize in this particular problem which one are we using. Now remember, the equation is the, this should be delta H. I've got to fix that in here. It's the delta H of the reaction times either the moles or the mass. And in this particular case, if you look at our delta H's, they're kilojoules per mole. So we need to multiply by the delta H of reaction times the number of moles. So that's a problem because they give us 248 grams of H2O. But that's something you've been spending 2 years doing mass to mole calculations. So this one's pretty straightforward. But remember, we should use the unrounded value because we're going to use this mole amount in a subsequent calculation. So we know that's how many moles of water we've got. We can plug that into our equation. 6.01 kilojoules per mole times 13.778 moles is going to end up giving us 82.8 rounded to 3 significant digits. And remember, our units here would be kilojoules because we started in kilojoules per mole for the enthalpy change. So that's a typical example of a change of state problem. You're multiplying the correct delta H, depending on whether it's melting or boiling or freezing. And remember, freezing, they're still only going to give us the heat of fusion. You've got to remember the heat of solidification is the opposite. So if it said how much energy does it take to freeze 248 grams of water at 0 degrees Celsius, then we'd still use 6.01, but we'd use it as negative 6.01 in our calculation. Now, the second regions that we see on this graph are our single state regions. We're warming up a single state. A to B, C to D, and E to F, all we're really doing is increasing the temperature of a single state. Sometimes ice, sometimes liquid, sometimes steam, but it's a single state situation in these regions. And you'll notice the temperature is changing, so when we're adding this energy, it's going to be speeding up the molecules, which is changes in kinetic energy. Now, if you recall when we did this calculation, back in chapter 5, we used the Q involved in warming something up or cooling something off as MC delta T. And remember, the delta T is where the sign is going to be established here. In the previous problem, in the change of state calculation, remember, you're the one who's got to determine whether it's a positive or negative sign based on the situation and whether energy should be going in, like when you're melting something, or energy should be removed, exothermic, like when you're freezing something. In this case, the delta T, the final temperature minus the initial temperature, is going to determine whether it's endo or exo. So this is slightly easier to get the right sign in. But it's just the mass times the specific heat times the temperature change would be the equation that we use. Now, a typical example of problem of this, like we did back in chapter 5, would be calculate the energy needed to warm 248 grams of ice from negative 12.0 degrees Celsius to 0.0 degrees Celsius. It's still going to be ice through the whole thing, so we have no change of state. All we're really doing is warming up the ice. Now, notice I've got my same set of constants, but in this case, we need to realize, since we're using MC delta T, and this is ice, we need the C for ice in our calculation. So 248 grams, C has joules per gram Kelvin, so we're fine to leave that in grams. We don't have to change it to moles. And then our constant for ice is 2.03 joules over gram Kelvin. And remember, changes in temperature are the same in Celsius or Kelvin, so I know you see 0.0 minus negative 12, and you're thinking, wait a second, those aren't Kelvin. Yes, I could add 273.15 to both of these numbers and subtract, but I'm still going to get the same thing. I'm still going to get a positive 12.0. And that would be Kelvin. So when I multiply that out and round to 3 sig figs, I'm going to get 6,040. But now notice I'm in joules, not kilojoules. Every time we use C's, they're going to be in joules. Every time we use delta H's, they're going to have kilojoules. So be careful of that unit difference, because that's going to be a problem when we have a complex energy calculation. So this is exactly what we did in chapter 5. There's nothing new here. Now, complex energy problems involve 2 different situations or more. What happens if we're doing things that involve change of states as well as single states? Well, we're going to have to use a combination of these 2 calculations. And remember, we've got to choose the appropriate C's when we're using Q equals MC delta T, and we've got to choose the appropriate delta H with sign when we're doing a change of state situation. And we also have to recognize that while normally we're multiplying by moles in a change of state, if they give the delta H as a heat of reaction rather than a molar heat of reaction, it'll be in kilojoules per gram. So we would multiply by grams, not moles. So always watch your units with these things. Now, in a complex energy problem, we're just going to be using combinations of these 2 calculations. Then once we know all the individual steps of energy, we can add it together to get the total energy involved in the situation. So let's take a look at how we would start to set up a problem like this. How much energy does it take to heat H2O from 12.0 degrees Celsius to 109.0 degrees Celsius? Now notice it's giving us water, and we're supposed to know the freezing point and the boiling point of water. If it's anything other than water in the problem, they would tell you when our change of state temperatures are. But for water, they're never going to give you that information. Now, when you go to set up this problem, it's very important that the first thing you do is set up a temperature versus time graph. And once you've got that set up, that's going to lay out the problems for us. So this is a critical step to be able to do. So really, we're not going to do this problem. We're just going to walk through this temperature time graph and see how that tells us what equations we're going to be using. So first, we set up our temp time graph. First thing we're going to do is put in our initial temperature. It says we started at 12.0. So I'm going to put 12.0 on my graph. We finished at 109.0. So up top, I'm going to put that. That's our ending temperature. And notice we're starting low and going high. So we're going to begin at our 12.0. Now the question is, in between these two, do we have any change of states? Because remember, change of state isn't going to be an increasing or decreasing line. It's going to be a flat line at our change of state in the temperature time diagram. So the next thing we need to do is ask ourselves, in between these two temperatures, is there a change of state for H2O? And the answer is yes. Water boils at 100 degrees Celsius. So I need to establish approximately where that is in our graph here. And don't worry about having it the exact right. It's just going to help us set up. Now, we know at 100 degrees Celsius that that's going to be a flat line. So I'm just going to draw a flat line to start with here. Now, at the beginning, we've got to go from 12.0 up to that flat line. So our first region here is going to be that. Then we're going to have our plateau, our flat line, where we're going through our change of state. After it's all boiled, now we're going to go through another increase again. So we just move it uphill to our 109.0. And you can see in this picture, we clearly have 3 different regions. So this is going to involve multiple calculations. Now, one thing that you should always know at the beginning of a problem is, should it be positive or negative for all of our Q calculations? Because you can really avoid simple mistakes if you recognize that from the very beginning. Well, in this case, we're going up in temperature. We're adding energy to the system. That's endothermic. Endothermic is positive in nature. So yes, all of our Q calculations should be positive. And that's something you should know up front and always process and think about it. Second thing you need to be able to do once we've got our graph set up, after you've determined positive or negative, is think about how many energy calculations this is going to involve. We've got 3 different regions, so that means 3 different energy calculations. Now I put 3/4 because remember at the end they're asking the total amount of energy. So we've got to actually do a 4th problem, which is just an addition. But be careful with that addition because you're always going to have to watch your units. Now, to actually look at our regions, region 1 here, if I stay on that graph, region 1 right here is going to be a change in temperature situation. So that means we're using this equation. Region 2, what comes next? Well, we've got no change in temperature, so we're going to use our other equation. And then region 3, the last region, once again, is another temperature change. So that's also going to use a Q equals mc delta T. But remember, the Q's will be different because while the masses are the same, the specific heats and the temperature changes are going to be different in regions 1 and 3. So that's in general how you'd set this up. Now let's look at a specific problem. So here's our complex energy problem. Calculate the energy needed to warm 248 grams of ice from negative 12.0 degrees Celsius to 99.0 degrees Celsius. Once again, we've got all of our same constants. First thing we're supposed to do is we're always going to start by graphing it, because that temperature time graph is going to help us set up the problem. This is a critically important step. Now, the first thing you do in your graph is you put in your initial temperature. We started at negative 12, so I'm going to put that down at the bottom. We finished at 99.0, so I'm going to put that up at the top. And then we need to ask ourselves, between these two temperatures, is there a temperature or is there a change of state for H2O? And yes, water is going to freeze at 0 degrees Celsius. Ice is going to melt at 0 degrees Celsius. So our temperature change between negative 12 and 99 is at 0 this time. Yes, there's another temperature or change of state at 100, but we don't get to 100. So those are our 3 important temperatures here. Now, first thing is draw your flat line for your change of state. So we're going to put a flat line in the middle. Now, we start at 12.0, so we're going to go uphill. I'm sorry, negative 12.0. So we're going to go uphill from negative 12 to our 0. And then after it's all melted, once again, we're going to go uphill from our 0 to 99. So it looks very similar to the last one in that we really do have 3 different regions. First, we're going to be warming the ice, and that's going to be a specific type of equation. Then we're going to be melting the ice in step 2. And then in region 3, we're going to be warming the water. So we really have 3 different things that we're doing here. Oops, looks like I have an error in my animation here. Now, what happens in those 3 steps? That's where the calculations come in. And some of these should look familiar because we already did them, so that's going to speed up things. So region 1 was warming ice. When we're warming the ice, what are we really doing? Well, warming ice is a temperature change situation. So it's a single state Q equals mc delta T situation. And in this case, we've got ice. Now, the reason I animated this so quickly is this should look very familiar. This is exactly what we did in our single state energy, or in the number 2 situation. So we've already done this calculation and already seen the answer here. We're going to get to 3 significant digits, 6,040 joules. But remember, since we're going to be doing an add of our energies, we need the unrounded value there. So that 6041.28 with the 4 underlined, reminding us that that's where it should be rounded to, that's what we're going to end up using in a minute. So that's how we calculate region 1. As a single state, it's a Q equals mc delta T. We've got ice, so we need the C of ice, and we need the temperature change when it's ice. That's 0 minus negative 12, which would be a positive 12. Positive, just like we said it would be. Second region also should look familiar because this was our energy problem number 1. We already looked at how much energy it would take to melt this ice. It's a change of state problem, so that's our delta H of a specific reaction times the number of moles, because in this case it's kilojoules per mole. And we're going to pick positive because we are talking about melting it, so that is the fusion. Remember, if this was freezing, solidification, we'd have to choose negative 6.01. Now, since we do need moles in this calculation, we had to calculate our moles again. And then from there, we can plug it into our equation to calculate Q. Positive 6.01 times 13.7778. And then rounded to 3 significant digits, we'd get 82.8 kilojoules. Notice this is kilojoules. The last one was in joules. That's a problem when we go to finish things, so don't forget that. And then finally, we have region 3. In region 3, we're back to a single state situation as we warm up the water. So that's back to a Q equals mc delta T. But now we need the C of water and the temperature change that water went through. So that'd be 99 minus the 0. And now we've got to use, for the C, we've got to use the 4.18 value. And since it's joules over gram Kelvin, remember our mass needs to be in grams, which it already is. And don't forget, temperature change in degrees Celsius is the same as the temperature change in Kelvin, so don't worry about the K there. And this would be our energy for this region. And this is not a calculation we did before, so make sure you carefully copy this one down. Now all that's left to calculate the total energy is to add together our 3 energies. So remember, our 3 energies look like this. This was Q1, that was melting or warming up the ice. Q2 was melting the ice, and Q3 was warming up the water. Now the biggest thing you need to recognize is our single states are in joules and our change of states in kilojoules. We've got to fix that before we try and add them together. And the easiest way to do this is just to change everything to kilojoules, because we're going to end up with more normal, smaller numbers then. So change to kilojoules, this is what we've got. So add them in your calculator and round appropriately. Hundredths, tenths, and ones. Looks like I've got a round to ones. So my calculator answer should be rounded to 191 kilojoules. And that would be the total energy. Now remember, as bad as this can get is potentially a 5-step problem, because we actually could have taken it all the way to the boiling point and then boiled it and then warmed up the gas, and that would add 2 more steps to the problem. The other thing you need to realize is if we started at 99 and went down to 112, then we would have, change colors here, a downhill to start with, then our flat line, and then a downhill to finish. And all of our values would end up negative. We'd have to choose a negative 6.01 for our solidification in the last region here. We'd have to choose a negative 40.67 for our vaporization. Oops, nope, we're not doing vaporization in that problem. All we're doing is the change of state. I pointed that to the wrong place. So this is actually going to be right here in region 2, and we'd have to choose a negative value. And then in these 2 regions, we'd be using the Q equals mc delta T, but our delta T's are now going to give us negative values, and all of our energies would end up negative. They'd have the same magnitude, but they'd just be negative. So if we were going from 99.9 to negative 12.0, we'd end up with negative 191 kilojoules. And that would be how much energy needs to be removed from the system in order to cool it off, freeze it, and then cool it off and end up with ice at negative 12. And that ends our set of notes.